Hello everyone, welcome to the Microeconomic Theory course on 31st March. In the previous class, we had discussed sequential move games or dynamic games, and we discussed how we could apply the backward induction logic to pick the Nash equilibrium in the sequential move game, which would be much more appropriate way of thinking what would be the right play of the game, right? So and we classified those subsets of Nash equilibria which satisfied backward induction as subgame perfect Nash equilibrium. Okay. So today we will continue with the discussion on subgame perfect Nash equilibrium in contexts in sequential move games where we would not be able to apply backward induction logic. Now, before I start that topic, I wanted to talk a little bit about the simultaneous move games that we had covered earlier. So let's consider the classic simultaneous move game that we have covered, which is, say, the prisoner's dilemma. Now, what we had done was the normal form expression of the game. So we had two strategies for each prisoner. So cooperate, not cooperate, say for prisoner number 2, and for prisoner number 1, cooperate, not cooperate. And the payoffs were, say, 3-3. If player 1 cooperates and player 2 doesn't, then player 1 gets punished say -2, 5, and similarly 5 -2, and then 0-0, right? And this had a unique Nash equilibrium, which was this one. Okay, non-cooperate, not cooperate was the unique Nash equilibrium when this game. So this is a simultaneous move game, and this is the normal form expression. This is the this is the normal form expression of prisoner's dilemma. Now, we had in the previous class talked about the extensive form expression, the sort of the tree form. Now, that form you can use to also express the simultaneous move games. We had used the tree form in the previous class to express sequential move games, but we can also use the same form to express a simultaneous move game, right? The same way we can express a sequential move game in matrix format. So in the normal form, we can do the other way around. We can express a simultaneous move game using the extensive form. So how do we express a simultaneous move game using a tree form, right? So there is the way. So we say that suppose player 1 moves. So this is player 1 or prisoner number 1. So this is the same prisoner's dilemma game we are which is a simultaneous move game, which we are expressing using extensive form expression. So we say prisoner number 1 has two strategies: cooperate, not cooperate. And for each possible strategy that player number 1 can choose, player number 2 can also choose to cooperate or not cooperate. So even when player number 1 chooses not cooperate, even then player 2 could choose cooperate or not cooperate. Now the problem is the following: if I stop here, then this looks like a sequential move game, that first 1 moves, chooses C or NC, and then 2 observes that choice and then decides whether to choose C or NC. Okay, But that's not the game, right? The game is that they both choose their strategies simultaneously. The way we express it in extensive form is by connecting these two nodes by a dotted line. What does this dotted line imply? It implies that one does not know when one is moving in this node. One does not know. I'm sorry, I said it wrong. One knows, of course, and at this node which strategy that it will choose. This dotted line here signifies that 2 does not know which node it is sitting on. Is it sitting on the top node or the bottom node? When 2 moves, 2 makes a move. 2 just knows that 2 is in one of these two nodes. Okay, so when 2 gets to move, 2 realizes that it is either in this top node or it is in the bottom node. What it doesn't know is whether which of the two nodes it is sitting on, because if prisoner number 2 knew which node he is sitting on, then that would have made the game sequential move, because then would have observed whether one has chosen C or NC, right? If 2 knew which node he is sitting on. By connecting these two nodes by a dotted line, we signify that 2 is unaware which node of the nodes that are connected by a dotted line, which specific node the player is located at. Okay, so that basically implies that when 2 makes a choice C or NC, 2 doesn't know whether one has chosen C or NC. 2 doesn't know, because 2 knows it's one of the two nodes basically. So that makes the game simultaneous move, right? So when 1 is moving, 1 doesn't know what 2 has chosen, because I've made 1 the first mover in some sense, and 2 doesn't know which node it is sitting on. So basically 2 doesn't know what 1 has chosen when 2 is making a decision, right? So let me just complete writing the game by writing the payoffs. So it is 3, 1 chooses C, 2 NC, then it is -2, 5. 1 chooses NC, 2 chooses C, then it is 5 -2, and finally it is 0, 0. Okay. So now this is an extensive form expression of the same game. Okay, so the same prisoner's dilemma game we can express using extensive form by using this dotted line to signify that 2 doesn't know which one of the nodes of all the nodes that are connected by a dot that the player is sitting on. Okay, this set of nodes that are connected by a single dotted line is referred to as the information set. So this set of two nodes, this set of two nodes is called one information set, and 2 is aware that it is sitting in that information set, but it doesn't know which specific node within that information set that it is sitting on. Okay, so this connected set of nodes are referred to as information set. This set of connected nodes are referred to as information sets. Okay. So to be precise, information set is a collection of nodes where a player can make moves and so information set is a collection of nodes where a player can make moves and the player is unaware of the specific node within the information set, unaware of the specific node within the information that he is located at. So information set refers to a collection of nodes where a player can make moves. So it refers to a set of nodes where the same player can make a move. And the other feature of the so what is the specific feature of this collection of nodes? The specific feature is that the player who's making moves in all these nodes is unaware which one of these nodes that it is located at, right? So it only knows that it is located in one of the nodes in the information sets, but which one specifically the player doesn't know, right? So now there are, of course, you can treat one specific node where the player knows that it is located at to be a trivial information set. So an information set can have only one node. So for example, let me go back to this extensive form Prisoner's Dilemma game. So player 1 is knows that player 1 is sitting in this node. So for player 1's information set is just this node. Okay, so player 1's information set is just this node. Player 2's information set is this set of two nodes. Okay, so for one, the information set is kind of a trivial information set consisting of only one node. So basically player 1 knows where he is located. Player 2 doesn't know where he is located. Okay, now of course in this game, because it is simultaneous move, it doesn't matter whether you make one move first and then make two moves second or the other way around, because in either way one player wouldn't know what the other player's choice is when the first player makes his strategy choice, right? So when player 1 makes a move, player 1 doesn't know what 2 has chosen, and when player 2 makes a move, player 2 doesn't know what 1 has chosen, right? So and that's what makes the game simultaneous move. So it's not that they're literally moving simultaneously, but that they're unaware of the other player's move when they make their choices. Okay, so in that sense, the ordering of player in an extensive form expression of a simultaneous move game would not be that important, right? Now so now that you have some idea about how to express simultaneous move games in an extensive form expression, and you have mentioned this idea of information sets. Let me talk about a game which is part sequential, part simultaneous. Okay, so it's basically a sequential move game, but there is a simultaneous move game which is built inside a sequential move game. Okay, so let me draw this game. So suppose suppose player 1 moves first, it can either move U or D. If it moves D, the game ends right away, 2,6. If it moves U, if it chooses U, then 1 moves again, and the choices are A and B, and then the choices for 2 is, so then there is a player 2 that moves, and the choices are X, Y, X, Y. No matter whether one chooses A or B, two can choose X or Y, but there is this dotted line. So 2 doesn't know, 2 knows that it is one of these nodes. Okay, so 2 knows that it is sitting in one of these nodes. 2 doesn't know which one of the 2 it is sitting on. Okay, so 2 knows that, so basically what does 2 know? 2 knows that 1 has chosen U. That much 2 knows, because if 1 had not chosen U, 2 would not know that it's his time to move, right? Because the game would have ended right away if 1 had chosen down D. If the fact that 2 now gets a chance to move, 2 knows that 1 has played U, but then 2 doesn't know what 1 has chosen after choosing U, either whether A or B. Okay, so when 2 makes a decision sitting in that information set, 2 is unaware whether 1 has chosen A or B. Okay, let me write down the payoffs. The payoffs are 3, 4, 1, 4, 2, 1, and 2, 0. Let's look at this game. This is a game which is sequential move. Why? Because first 1 makes a move, then 1 makes another move without knowing what 2 is doing, and 2 also makes a move without knowing what 1 has done after choosing U. Okay, so this is a sequential move game because there is partly there is a sequence because 1 has to move twice, but once player 1 chooses U, then there is a simultaneous move game happening within that sequential move game, right? So in these kinds of cases, so this is an example of a game where you cannot apply backward induction. Why is that? Because the logic of backward induction requires that every player must know which node exactly where they're sitting on every time they make a move, right? Otherwise, it may be hard to apply backward induction. Sometimes you can apply backward induction when there are these non-trivial information sets, when there is simultaneous move games built inside a sequential move game, but in many cases you would not be able to, because imagine two trying to make a move at this information set. 2 is trying to make a move at this information set. In this information set, 2 doesn't know whether it is sitting on the top node or the bottom node. So whatever strategy choice that 2 has to make, whether say X or Y, it has to think that it can be either on the top or the bottom, right? It cannot have one strategy choice for the top node and another strategy choice for the bottom node. Imagine our definition of strategy that I discussed in the last class. I had mentioned that a strategy must specify a full plan of action. So it must say what a player is doing in each node that it can make a move on. However, in this specific case, in cases where there are these information sets consisting of multiple nodes, the player has no way of specifying that I will choose X, for example, when 2 is sitting on the top node and 2 would choose y if 2 is sitting on the bottom node. 2 cannot have a strategy like that because 2 doesn't know whether it is sitting on the top or the bottom node, right? So it can have only one strategy per information set. So let me now augment our definition of our definition of strategy. So in the last class, the definition of strategy was that it must specify an action in every node in which the player can make a move. Okay. But that definition pertained to cases where there are no non-trivial information sets. There are only information sets which are one node, consisting of only one node. So basically those games are games where players have no uncertainty about which node it is sitting on, which node they are sitting on. Okay. But in games that is currently in front of you, there is at least one player who has some uncertainty about which node the player is sitting on. So in these games, the definition of strategy would be augmented. Basically, the definition of strategy would say that a strategy for a player must specify an action for every information set in which the player can make a move. Okay. So definition of strategy. So definition of strategy is now augmented in presence of these non-trivial information sets. So now we say a strategy for a player must specify an action for each information set in which he makes a move. Okay. So that's now so instead of specifying an action for each node, you have to now specify an action for each information set. Remember, for players who know where they are sitting on, which node they are sitting on, that node becomes their information set. So those are trivial information sets. So this definition now is applicable to our previous year in the last class games as well, right? Because in the last class games there was no non-trivial information set, so everybody knew which node they are sitting on. So everybody's information set was their singleton nodes. Okay, so in that sense, this definition subsumes our previous class's definition. Okay, so that's what I'm saying, that our current definition is an augmented version of our previous definition of strategy. Okay, so now what is strategy? So strategy for player 1 is to specify something in the initial node, in the first node, and then specify something in this node. Right? These are the two nodes or two information sets, trivial information sets, in which player 1 makes a move. And for player 2 must specify an action for this entire information set. 2 must say that when 2 reaches here, when it's 2's chance to move in this information set, 2 must say a specific action. Either say 2 would choose X, meaning it would choose X no matter whether it is sitting on the top node or the bottom node, or it can say it is choosing Y no matter whether it is sitting on the top node or the bottom node. It will just say I'll choose Y in this information set. Okay. So that's the idea of strategy in this game. Okay. Now that we have defined the strategies in games where we cannot apply backward induction, let us now discuss how would we apply the concept of subgame perfect Nash equilibrium in these kinds of games, because the equilibrium concept that we still want to apply is subgame perfect Nash equilibrium. We still want to find out what is the subgame perfect Nash equilibrium strategies of this game, but we can't now apply it backward induction, so we have to use some other other method to apply backward some SPNE. So that's in the next video.